Welcome to our lecture online. Now let's answer the question, what is a Taylor series? Well, it's another form of an infinite series, but let's take a look here and see how we can derive the format of the Taylor series. And then later on, of course, we're going to see how to actually apply the Taylor series. But let's start with the general form of a power series. Now, by now we should be familiar with this, that f of x can be written as c0 plus c1 times x minus a plus c2 times x minus a squared plus c3 times x minus a cubed and so forth, noting that every one of these constants can be different. Now they could be the same, it's still a power series, but a power series allows for each one of these constants to be a different number. Now, if we're going to evaluate this power series for f of x equals a, notice that when x becomes equal to a, every one of these terms goes to 0, and the only surviving term is c sub 0, so the function evaluated a is equal to the first constant in the series. Now let's take the derivative of that, so we get f prime of x, and notice that the constant then goes away, the derivative constant is 0, and now we end up with c1 plus 2c2 x minus a plus 3c3 x minus a squared. Simply, we take the exponent, put in front, subtract from the exponent, and then take the derivative of what's inside, which of course is equal to 1, and we end up with this power series right here. Now notice that if we evaluate f prime of x for x equals a, all these terms go to 0, and we just get c1. So the derivative of that power series, f prime evaluated a, equals the second constant. Now we take the derivative again, the second time. The second derivative of the function is equal to 2c2 plus 6c3 times x minus a. Notice 2 times 3 is 6, so we get 6c3 x minus a to the first power times the derivative of what's inside, which is 1. Here we get 3 times 4, which is 12, c4 x minus a to the exponent 1 less, and so forth, and we get our new power series. Now note here that if we evaluate the second derivative, when x equals a, all these terms go to 0, we end up with 2c2, which means the second derivative evaluated a gives us 2c2. Now you probably get the hang of this. We do it again. We take the third derivative and the fourth derivative and the fifth derivative. So when we take the third derivative, we get 6c3 plus 24c4 x minus a. Notice 2 times 12 is 24c4, x minus a to the 2 minus 1, which is 1, times the derivative of what's inside. And we continue. Notice that if we now evaluate the third derivative for x equals a, we get that to be equal to 6c3. Now you begin to realize that we have a way of establishing the constants in each one of these. We can establish c1, c0, c1, c2 in terms of the derivatives of the function evaluated at x equals a, which means that c0 is equal to the function evaluated at a, c1 is the derivative of the function evaluated at a divided by 1 factorial, which of course is 1, c2 is the second derivative evaluated at a divided by 2 factorial, which is 2. c3 is equal to the third derivative evaluated at x equals a divided by 3 factorial, which would be 6. c4 is equal to the fourth derivative of the function evaluated at a divided by 4 factorial. And then you begin to see that the general form of all the constants in the power series can be written as c sub n is equal to the nth derivative evaluated at a divided by n factorial, which allows us to find the constants of the entire power series, all in terms of derivatives of the power series. So since we can write a power series as the infinite sum from n equals 0 to infinity of the constant c sub n times the quantity x minus a to the n power, which, since we now have an expression for c sub n, which is right over here, we can plug that in. It's equal to the nth derivative evaluated at a divided by n factorial times x minus a to the n power. And now when we expand that, it will look as follows. F sub x of f of x, the original power series function that we started with, can be written as f of a plus the first derivative of a divided by 1 factorial times x minus a, plus the second derivative evaluated at a divided by 2 factorial. Remember that these are always the constants. That's c0, this is c1, this is c2, this is c3, multiplied times x minus a squared, x minus a cubed. So we've now taken the general form of the power series and written it in such a way that we can now evaluate the constants of each of the terms. This new form of the power series is called the Taylor series. And more specifically, it's called the Taylor series of the function f of x, because it's another form of the very same power series function, but centered around a. That's why we have the x minus a here. So that's a very special form of that power series called the Taylor series. And yes, there are very useful ways in which we can use that Taylor series. We'll see one more series in the next video, and then after that we'll see how to apply those various new forms of the power series to come up with some interesting things. So stay tuned. That's how we do that.